Okay, so let's go finish this chapter on op amps. So where are we at? Damn. Here
I
we
see
go.
that hammer, Edgar.
Yeah. Okay, that's pretty funny. Okay, so here we are. So we're looking at example 5.3. I think that's what we were on. And this is called a summing amplifier. And one of the things that we want to do here is that I want to show you another technique for solving these circuits, is that we want to talk about source transformations, simple circuits, and then we will do node. I think this might be the last time I do node. Okay, it's just, there's, yeah, I mean, it's just like, do I want to keep doing node? No, I don't. So we'll see how it goes, but I'll do it on this one, and then the rest of them, I might just set it up and show you how to do it, but I won't actually do it. So the first one that we want to do here is that we want to do it with source transformations. So to do that, I'm going to go get a copy of the circuit, and we want to use source transformations here. These are totally legit on these circuits here. And so what we want to do here is that you can see that when I look at the circuit, you could see that right here, I have a resistor in parallel. And another thing that you also see here is that if you look, this is ground right here. This is ground. So when I look at this particular node right here, you could see that these two 6K resistors are in parallel because they're connected to the ground. So one of the things that we can do here is that I could then treat this as a 3K resistor, right? 3K resistor, which is then connected to the ground. And then I could do a source transformation on this here. So if I do a source transformation, and a resistor reduction, what do I see here? Well, the source transformation, you could see that I'm going to convert this guy. Well, I'm going to convert that into a current source. And if I convert that into a current source, what I can do here is that then I'm going to have a 6 and a 3 in parallel. So that means then I'm going to have a current source that looks like this. And of course, this guy's going to be 2 amps or 2 milliamps. Right? And then this guy's going to be this guy right here, which is a 6K. And now I have a 6K and a 6K and a 6K, where I have 3 parallel 6Ks. So now in the end here is that I really have a 6K, a 6K, and a 6K. So I'm going to get, of course, a 3K here. And then this is half, so then that's going to give me, right, half of, so I divide by 3. So then this is going to give me what? A 2K resistor here. Right, am I doing that right? I'm going to get, let me make sure. Oh, no, no, no. Am I messing up? Oh, dude, I messed up. I don't need to do that as a source transformation yet because I'm thinking ahead. I don't want to do that. I don't want to do a source transformation. I think that would be too much work. Because what ends up happening is that when I look at this resistor, I have really these guys connected to ground, and this is a 6K, and this is a 6K. So this becomes a 1 resistor, which is a 3K connected to ground. So why would I say source transformation? I don't need to do a source transformation. I need to do a resistor reduction. And so then the circuit then looks like this here. I'm going to have a 12 volt, a 6K, and then I'm going to have a 3K. And that 3K is connected to the ground, which then tells me that I have a 6K here. And so this node right here then is, of course, V out, and then this is the current I out coming into here. So I could do a series of source transformations. I think this is the easier thing to see. So I just recognized that that 6K and 6K were in parallel. So that's what the circuit looks like. But could I have done source transformations? And would I get the same thing? So if you look at the circuit in the end, what's it going to look like? It's going to look like this here, which is 12 volts. Then I'm going to get a 9K. Then I get my op amp, and it looks like this here. So that's what that circuit looks like right there. Now, can I get the exact same thing with source transformations? I better. So if I do a source transformation, then I'm going to really do a source transformation on this guy. So I'm going to get a 2K. Okay. So if I do that, I'm going to get a source transformation that looks like this. So I have a current source, which should be, what is that? That's got to be, that has to be 12 divided by 6K. So it's got to be a 2 milliamp source. Now I have a 6K. And then I have another 6K plus this 6K. So that's what my transformation looks like. And if I continue to do that, of course, this is a 3K. So then I should get, so if I multiply both of these together here, why am I not getting, why am I not getting 12 volts? Okay, do I have a mistake here? Where's my mistake at on if I try to do a source transformation on this? Because I'm getting a voltage that's going to be 3K times that is I'm going to get a 6 volt, which is then going to give me a 3K and a 6K. So this circuit and this circuit are not matching up. So obviously I have something silly going on here. Oh God. This is, right? I'm not really sure what's wrong. Which one do I trust more? I have a tendency to trust this more because I must be doing something silly in the one above because this source transformation is pretty obvious. So what am I doing wrong? So here's what I'm going to do. Since I trust the second one more, I'm going to just solve this second one. And then when I go do the simple circuits one, we'll compare both of these with the source transformation. So what I'm saying here is that the final circuit reads that I have a 6-volt source. I have a 9K resistor connected to the op amp. This is connected to the ground. That's connected to the ground. This is a 6K. So then I know that this is V out and this current is I out when this is 6K. So then I'm just going to follow the current here. If this is ground, then this is ground. So I know that if V2 and that's V1, so I know here that V2 and V1 must be the ground. So when I look at the current here, that current must be flowing in which direction? It must be flowing in that direction right there. So what I'm going to do then is that I could get that current through that 9K resistor. So from Ohm's law, I know that the current through that 9K resistor has to be 6 divided by 9. So I should get 2/3 milliamps. But since there's no current going down here, then that means that that green current continues to move through the 6K resistor. So again, I'm going to apply Ohm's law at 6K resistor. And maybe I should have done this right here just to be a little bit more clear. Maybe I should say Ohm's law at 9K resistor. I get this, but I now know that the current between the 9K and the 6K must be exactly the same. So if I look at this thing, then I see here that if I apply Ohm's law, then it says that V1 minus V out has to equal 6K times the current of the 6K, which of course is then going to be 6K times 2/3 milliamps here. So I then get what? I'm going to get 4 volts, sorry. So now solving for if I solve for V out, what do I get here? I see that V out is then going to be V1 minus 4, right? And V1 is 0, of course. So I'm going to get minus 4 volts for V out. So I now have the voltage V out. So to get the current here, I'm going to apply KCL at this node right here, at the output node. So now I'm going to apply KCL at output node. And what you're seeing here is that I'm getting what? I'm getting the current of the 6K resistor coming in. I have the current of the out, which goes into the op amp, and then I have a second current. Well, I know that this node here is 4 volts, negative 4 volts, right? I know that that node V out is negative 4 volts. So that means here is that the current is coming from the ground for this K resistor. And I'll put a prime here to just differentiate about that. So it has to be coming from the ground. So if I apply KCL to this, all of the currents in must equal the current out. So then I'm going to get that I out must be I6K plus I6K prime. So I already know what the 6K resistor is, and that is 2/3 milliamp. And then I'm looking at the 6 prime here. So this guy is going to be 0 minus 4 divided by 6K. Well, that's also 2/3. So I should then get 4/3 milliamp for the output current. So I have both the voltage and the output current. Now I got to go check this and see if this works for, God, I don't know what happened here. I must be doing something silly. I want to go do simple circuits here. So then this is method 2. So I want to, this will tell me whether what I did was right. So I'm going to stick my circuit back into here. And I'm not going to do anything but simple circuits. And I'm just going to follow what the current is doing here. So the first thing that I note here, again, this guy here is ground. This guy here is ground. So if this guy is ground, then I could use VDR right in here. I could come in here and I could focus on this guy and use VDR because, so for the circled, for the circled region, what you're really seeing here is that you're really seeing this thing here. This is 12 volts. Here's 6. Here's 6. Here's 6. But remember, this is connected to ground. This is connected to the ground. And they're all connected to the same ground. So that this here is really, these two guys here are in parallel. So if I use voltage divider rule, what I can do here is that I can redraw this circuit like this here, where this is 6 parallel to 6, which is a 3K, and this guy's a 6K, and this is a 12 volt. So if I do that, then I could calculate what the node voltages are, right? I can go and I could calculate what this node voltage is right here. So I know that this voltage, of course, is 12 volts. And then at this node right here, I could go calculate what that voltage is. So what I'm going to say here is that that voltage at this node right here, so what is that node voltage? Well, it has to be the voltage drop across the 6K here. So if I look at this thing, so if I apply VDR across the 6K, then I'm going to get that the voltage of the 6K is then going to be, of course, 6 plus 6 plus 3 times the voltage, which is 12 volts, So that's what's 2 over that. Is that's 8 volts, right? So 6 over 9 is 2/3. Yes. So this is 8 volts. So that means that this node right here is 8 volts right there. So that means then that the voltage drop across 3 would then be 4 volts. But we don't care about the voltage across the 3. We only care about that. So now what I'm going to do here is that I'm going to go back to the original circuit now. Okay.
Hey, Carlos.
I'm going to go back to the original circuit. So what do I have in the
Carlos?
original circuit? Well, what did I actually calculate right here? Well, let's look at the nodes here. We agree that this guy is 0. That's the ground. We know that this node right here is, of course, 12 volts. But we just calculated this node. And what is that node? It's what? 8 volts. So that is 8 volts. So now I can just use Ohm's law to calculate this thing here. So if
Hey,
I know
Carlos?
that that's 8 volts,
Yeah, this happens sometimes.
this is a 6K.
Hello. Yeah. Sound.
What?
You got a question, dude?
I can't hear anything.
Well, you can hear something.
Well, I just heard it right now, but very low.
Can you hear me?
Yeah.
So when we apply VDR across the 6K, it's 8 volts across the 6K. So shouldn't the node be 4 volts?
Yes. Sorry about that. You're absolutely right. We dropped, yes. So that means here that this has to be 4 volts. Thank you for the correction. It is.
Yeah, no problem.
So across the 6, but then we got to go across the 3, which would then be 3 over 6 plus 3 times 12 volts. So this would be 4 volts. So Josh is absolutely right. It is 4 volts. So if I have that, then I'm just going to follow the current. So I can see here that the current is going to go in which direction? It's going to go here. We know that the current in this branch isn't going to affect this current, so then that current is exactly the same. So if that's the case here, then what am I going to get here? So then the current across the 6K, the 1 6K that we're focusing on, you could see here that that's got to be 4 minus 0 divided by 6K, which is then going to give me 2/3 milliamp, which is exactly what we got up here. Right? Didn't we get 2/3? We got 2/3 here. So now that we have 2/3, then you could see here that then I just have the same game that we did before. So then if I want the voltage over this next 6K resistor, so the output voltage is related to the second 6K resistor. And what I mean by the second is I'm talking about this particular guy right here. Because we focused on this one when we were looking at the current, it would be that guy. And you could see that from Ohm's law, that tells us that it's got to go from 0 to V out, and that has to equal 6K times the current of the 6K, which is something that we already did. And from our previous discussion here, this should be minus 4 volts. And then, of course, we apply KCL, and then from our previous discussion on KCL, we saw that I out is then calculated identical, which would then be 4/3 milliamp. So that's how I would have done it with simple circuits here. Is just identifying that they had the common ground. Now the next method, which will then be the method of node analysis. So then we'll go to method 3, and we'll look at node analysis. So let me go back and look at this circuit right here. So if I'm looking at node analysis, I got to go, what are my known nodes? What do I know here? Well, for starters here, we know what this node is right here, because that's connected to the ground by a wire. So of course, we already know that V2 must be 0. We also know this node right here. And this node we know is 12 volts. So what are my unknown nodes here? Well, we know that we can't write an equation for the output node. So we know that this guy is the output, but we can't write anything. So then I have this node right here. Well, I don't want to use V1 and V2. So maybe I'll call this A. And then this node right here, I'll just call V2. So as far as we could see here, if I do the numbers here, there are 2 unknown node voltages. So one here is the node VA. One is the node V, it should be V1. We've already defined, V2 is the one below, so this should be V1. And then we need, we need the ideal op-amp model. So what I'm seeing here is that I have 3 equations, 3 unknowns. So in this case, I'm going to get VA, V1, V2. So let's go do that. So I have node VA. So then I'm going to go write all the equations for that. So I have what? 1, 2, 3. So I get 6, 6, 6 for VA. Then I have 1 connected to 12. I have 1 connected to the ground, and I have 1 connected to V1. So then I get 1, 6, V1, and no current sources, so that's 0. That's my first node. My second node equation is for node V1. So I could see that I have 2 resistors in connection. So I'm going to get 1, 6, 1, 6, V1. And then I have 1 with A. So I'm going to get minus 6 VA. And then I'm going to have 1 with the output. So I'm going to get minus 1, 6 V for the output. And you could see as of right now, I have 2 equations and 3 unknowns. And that's where the ideal model comes in. And the ideal model says that V1 and V2 must be the same. So in this case, we know that V1 minus V2, but we already know that, I mean, this is kind of silly, that, that this is really 0. And the difference between them is 0. So we can automatically see that V1 has to be 0. So when I really go back into the system here, I could put V1 into 0, or else I could just come in here and I could just go, well, I know that's gone. I know that's gone. So I really have 2 equations and 2 unknowns. And so what I'll do here is that then I'm just going to say that if you were to calculate this thing, we're going to get, of course, that V out is equal to minus 4 volts, just as expected. So that's how you would set that up and use the ideal condition to actually do that. Okay. I want to go into the next example. This next example I really like because it really helps you, I think, to actually see what is going on with when you go follow the current here. So what am I doing here? So the first thing that I want to do here is that my first method that I'm going to do is I'm going to do simple circuits. So I'm going to go in here and I'm going to say the method and I'm going to use simple circuits. So the first thing that I would look at here when I use simple circuits here is that I need to sort of like identify what's going on here. And the first thing that I would probably look at is that I would pick one op amp and then start moving in that direction. And you could see that I labeled that the output nodes I labeled as O1 and O2. So the first op amp I'm calling op amp number 1. The second one I'm calling op amp number 2 here. So this one here is number 1, and this other one, of course, is number 2 here. So I'm going to label these with different colors. So what I want to do here is that I'm going to focus on, op amp number 1. So let's go do that. So what I'm going to do here is that if you look at this thing, I'm going to look at the input of all of these. And one of the things that you see here is that these inputs here, they have to be the same. So if this guy is 10 volts, then this guy has to be 10 volts. But wait a minute, you could see that the input of 1 should also be 10 volts right here. So right away, what we're seeing here is that I know these voltages right here. So I know that this guy's 10 volts and I know that guy's 10 volts. So just by looking at one, I can identify that. And then of course, we know that this is my ground here. Now, if this is my ground, then that means here that there is a current that's flowing in this direction. So if all of these resistors are 10K, right? All of these resistors are 10K, then I know what the current of that resistor is. Because I could immediately see that the current here should be 10 minus 0 divided by 10, which is of course 1 milliamp. So now I know what the current is. But what that tells me here is that I now know that if I start to follow, I know that there's no current in this branch right here. So if I come in here, I know that the current here in this branch must be 0. Okay, so in this case here, that node is, I guess that's node 2. And you're seeing here that that current's 0. So I know that the current, so if that guy's 1 milliamp here, then I know that the current here is still moving in this direction. And this guy's going to be equal to what? 1 milliamp too. So just by looking at those nodes here, I know exactly what has to happen here. So I haven't even looked at the other nodes. So then just the first node, so I'm going to say that there's this blue node, and that leads to the output of node of op amp 2. And then this other one here, I have this node, which leads to here. So I know those currents are defined as IO1 and IO2. So now I got that. So now let's see here. What do I know about the currents here? So for starters here, I know that at this node I got 1 amp. So note, and I know that this resistor is 1 amp. So when I look at this node right here, you know what? I think I'm going to label nodes here because I think it's getting a little bit complicated without labeling them. So since I've been using 1s and 2s, I'll call this red node over here, I'm going to call this A. This green node over here, I'm going to call this B. So when you're looking at the current, so the current nodes A and B is connected to the voltage of the first op amp, right? So this is the output voltage of op amp number 1. So that means then I can calculate what that is here. If I do that, what I'm going to do here is that you could see here is that node B, I'm going to call that as 0, 1. So this tells me here that the current of that guy should be what? It should be VO1 minus 10 divided by 10K is going to be 1 milliamp. So this is telling me then that you could see here is that this tells me here is that the output voltage VO1 is then of course going to be, so if I multiply this out, I'm going to get 10 plus 10. So I should get plus 20 volts. So I now have the output voltage of that node. So I know node B is 20 volts. Now, wait a minute, but now I know this node right here. I know that that node, because of the way the wires cross here, that node is 20 volts. So then that tells me that the current is going to be going in which direction here? It's got to go from the high to the low. So I'm going to keep labeling these nodes because I'm going to have trouble. So then the node between B and C tells me that I have a current going that way. Well, you can see that that current, if this current in this branch, do I know what that current is? I don't. But I can calculate the current between B and C here. So now what B and C, the current is VB minus VC is going to be 10K times the current between BC here. So I know what B is. So this tells me that this is 20. Obviously, I know what the node C is, which is 10. And this guy's going to be 10K times this current BC, which then tells me that the current BC here is going to be 10 divided by 10, which is going to give me 1 milliamp. So now I have 1 milliamp going in that direction. Let me make sure I got that right. Right, the current between BC should be 1 milliamp. So then if that's the current here, then that allows me to apply to get this current, which I'm going to call, let me make this a little bit bigger. I'm going to call this current I1. So that's the current of the output thing. So now, here I go. So now I'm going to apply KCL at node B. So what I'm seeing here is that all three currents are going out. So I go I in equals I out. How many currents are going in? 0. So then I'm going to get the current I01. Then I'm going to get the current between BC, and then I'm going to get the current between BA. So this guy right here, BC, we already said was 1 milliamp. We already said that the current between BA is 1 milliamp. So this implies here is that the current going into the op amp is then going to be minus 2 milliamps. So I now have the voltage and current for the op number 1. So then my goal here is to go back and look. I'm going to copy it, and I'm going to bring it down here. So now we now compute the output voltage and get the output current for op amp number 2. So let me paste this guy here. Oh no, that's not what I wanted. Let me go back and try to get, oh, no. Well, I did a number on this guy. Here, I got to go get the op amp. So let me color these again real quick. So we call this red. We colored this red. This red.
So quick question.
Yes.
What are you calling node C? Are you calling node C the branch between op amp 2? Or like that blue line you're drawing now? Or is
So,
node C
the-
that little bridge between the two?
Here, you could see my reasoning here. So check this out. This is A. This is B. This is node C. And you could see that probably I'm going to call this node D.
Okay, so C is not on A, but you're drawing it as red, or
You
it
know, I'm
is on
drawing
A?
it at red because we know that because this is 10 volts, this is 10 volts. And because that's 10 volts, that has to be 10 volts. That's why I drew it that way. Because the red just indicates that they all have the same node voltage.
Okay, it's just that in the original circuit, it looks like those wires are laying on top of each other instead
They're,
of
they're
connected.
not. They're
Okay.
interacting. If they
Alright.
were laying on top of each other, then you would have seen me do something like this.
Good deal.
Okay. So I need to go back and see. So what I'm trying to do here is that I'm focusing on node 2. And by the way, there's another node that was this guy right here, which is of course the ground. So what I do know is I know this guy right here. So the first thing that I note here is that I know that there's no current along these branches right in here, right? So if I look at the current here, and I look at the current here, all of these currents are 0. So if I'm looking at the flow of the current here, the current is going this way at 1 milliamp. So therefore, the current coming here must be 1 milliamp too. So if that's the case here, then what we can do here is that what can we conclude here? So now what I want to do here is that I want to apply Ohm's law between C and D. So when you apply Ohm's law between C and D here, you can see here is that VC minus VD has to equal 1 milliamp times 10K. Sorry about that. So it has to be 10K times 1 milliamp, which is of course 10. However, we already know that C is at 10 volts. So we already know that that guy's at 10 volts. This implies then that VD must be 0. But VD is the output of op amp number 2, which is therefore 0. So op amp 2 has an output voltage of 0. So then if I look at this thing, so that really means that that blue is really ground. So right in here, I know that this is 0 volts. Well, check out the current here. If you look at the current, look at this current now. There's a current going here. It's a 10K over 10 volts. So I could then see that the current between the 10 volt and D. So now if I apply Ohm's law between 10 volts, maybe I should call that node E, just to make it clearer. And I'll say between nodes E and D, you're going to see here that this should be the voltage between E minus the voltage between D. And that guy has, over that, that's got to be a 10K divided, for that 10K resistor here. But wait a minute, I know that this guy is 0. I know that that node is 10. Therefore, that tells me that that current between E and D is also 1 milliamp. So now, if I apply KCL at node D, we can get we can get the output current IO2 of op amp number 2. So then KCL tells me what? Well, I have one current coming in, and that's 1 milliamp. I have the other current coming in, which is 1 milliamp. And then I have the current going out. And in this case, that's IO2. So then KCL tells me that IO2 must be 1 plus 1 or 2 milliamps. So now I have all of the output voltages and the currents. So the question is, how do you do this with node analysis? And I won't go through all the details, but I'll just set it up. So let me see if I can paste this circuit back into here. Okay, good. So what do I know here? Well, when I look at this thing here, I can't write, right? So when I look at, if I stick to the same color scheme, I can't write a node equation for this guy. And I can't write a node equation for this guy right here. Right? So cannot write node equations for green and blue nodes. Well, there's two nodes that we already know, right? One of these guys here is that, of course, we know what the ground is. And I know what this node is right here. And if I stay with the same color scheme, I know that this node right here is 10 volts. So what I'm seeing here is that this is my O2 node, O1 node, excuse me. This guy here is my O2 node, right? So if I'm looking at these nodes right here, so what you're seeing here is that the unknown nodes are only 2. So if I come in and I color these here, note that I don't know this node. So the purple is one of the nodes that I don't know. And then there's this other node right here. I don't know that node right there. So sticking with the same numbering scheme that I did before here, I'll call this node right here A, and I'll call this node over here C. So I have 2 node equations. So I'm going to, so if I do the counting, we have 2 unknown node voltages. So if I have these 2 unknown node voltages, note that, can I say anything about node op amp 2 here? Well, I know that for op amp 1, you could see that all of these, no, well, they're going to tell me about 2 right away. So I'm going to say that I have node VA. So if I look at node VA, I can see that I have 2 resistors. So I have 10, 10, VA. Then I have one with the ground. And I have one connected to the output. And of course, that has to be 0. And then if I go to node C, I have 1, 2. So I get VC, and then I have it with 1 is the connected to the VO2, and the other one is connected to VO1. And then this is going to be 110 VO1 is equal to 0. So what does the ideal model tell us here? Well, the ideal model tells us that VC must be 10, right? So if this is going to be V21, this is going to be V11, and that really comes from the fact that I'm setting these two nodes to be exactly the same, which then is the same as 10 volts. But if that's 10 volts, then it tells me what node VA is. So then if VC is 10, then we know that that's 10, and therefore this is 10. So this tells us then that because there's a short connected or a wire connected between V11 and in this case here, let me erase the 10, and I'm going to write this as V21, and this is going to be V22, and this guy must be 10 volts. So therefore, we could then say that because V21 has to be the same as V22, if one of them is 10, then that tells me immediately that VA has to be 10 volts. So what that tells me then is that now I could go calculate the voltages here. So I know VA is 10. I know that VC is 10. So if I replace these in these equations, I should have highlighted these guys just to make sure that we're clear. That's what the ideal model tells us here. So now you could see here that this is really then I'm going to get 10 plus 10 times 10 minus 10 VO1 equals to 0. And then I'm going to get 10 plus 10 times 10 minus 10 VO2 minus 10 VO1. So I now have two equations and two unknowns, which then will tell us what we already calculated before, that one of them is 20 and the other one is 0 volts. And so I get the exact same results. So that effectively ends all of the techniques for solving op-amp problems. So what we want to focus on now is we want to go in and I want to do what are known as design op-amps. That means you're designing what the output is supposed to be looking like. So this is called designing op-amp circuits. And typically what you find here, if you're going to design an op-amp circuit, is you want to essentially have, so what you're going to do here is that you typically want to do something here. You have a certain amount of inputs that are going to be coming in. So let's call this input 1, input 2, and you could have a series of inputs. And then this guy here is really your op-amp circuit. And the only thing you care about is some particular output. Now, what goes into that op amp circuit here really depends on what you want to do here. And one of the examples that I want to show you here is that this is what's in the textbook. And you can actually go in and look at these things here. These are the designer op amp circuits here. So when you're looking at this here, if you set up an op amp circuit with this type of resistors, you get an inverting amplifier. If you set it up this way, you get a non-inverting amplifier. Or you could have these summing amplifiers. The summing is going to be negative. The inverting summing is going to be a positive quantity, but you can look at ratios of these things. And it doesn't end there, right? I can have a circuit that looks something like this too. Other designing op-amp circuits may look something like this, where you have a difference amplifier, a current to voltage converter, a negative resistance converter. All of these kinds of things here. And the idea here is that can you use these circuits to actually do that? There are two really important ones missing from this. They're called the integrator and differentiator op-amp circuit here. So to give you a sense of what I'm talking about, I want to look at an example of something that we can look at together here. So as an example, let's say that you want to design this op-amp circuit so that the V output is always 5 times V1 minus 2 times V2. And so what you're seeing here is that these guys are the input voltages. So what you know here is that V1 and V2 are the input voltages. Right, and because they're the input voltages, what we want to do here is that we want to do two things. We want to, in the end, we want to subtract them, and we need to scale them in order to really do this process here. Now, there's a couple ways to actually look at this thing here. You could, so the first way that I approach this thing here is that my first goal is to first look it up online. Can I find a circuit that's already been designed to do that? And if that doesn't work, then I say my second attempt is to build it in stages. So if I go and I look at this thing, I need to be able, so the first thing that I want to do here, so if I look at this thing right here, I'm going to look for something that sums and subtracts voltages, voltage inputs. So if I come back and I look here, is there anything that does that? Well, the first thing here is that, well, I have an inverting amplifier, okay. Non-inverting, obviously the voltage follower, but here's the summing ones. And when you look at the sums of these guys here, note that this guy does not subtract, it adds them in the negative direction. Whereas this guy over here, it only adds them. So I can't really go in and do that. So we're going like, okay, that one won't work. And then I look at the difference amplifier and you could, oh, and you go like, hey, it does subtract them. But that's the problem here. This circuit here always has the same amplitude. Okay, always has the same amplitude. So therefore, that's not going to work either. So the goal then, my second goal here is that now, what am I going to do? I have to build this op amp. And I'm going to do it in stages here. So the first thing that you got to pay attention to is that note. So one of the key points here is that this has a difference with different gains. And that's really the issue here. And so one of the things that you could think about here is that you can do the following thing here. Is that if I use an inverting amplifier gives me a minus sign. So I could immediately start with the minus sign. Then I have to be able to convert, either keep the minus sign or convert the minus sign. And if I go with the summing amplifier, the sign will never change. But if an inverting summing amplifier, the sign will never change. But a summing amplifier changes the sign. So what I'm seeing here is that if I make a combination of an inverting amplifier with a summing amplifier, I can create a minus minus, which gives me a plus, and then I can create a second minus sign. So what I'm seeing here is that I'm seeing two stages here. So the first thing that I want to do here is that I'm going to use an inverting amplifier to create a minus 5 volts. Or minus, not 5, but a minus V1. And then what I'm going to do here is that now I'm going to use a summing amplifier to sum two voltages. In other words, I know that the summing amplifier always gives me an overall minus sign. So if I sum minus V1, then I'm automatically can create a V2 like this. And so in the end, I'll get a positive V1 minus a V2. So let's go do that. So the first thing that I'm going to do here is that I'm going to use an inverting amplifier. So what does the inverting amplifier look like? Well, it looks just like this. It's like exactly like the one we did in lab. So here we go. So the first thing that I'm going to do here is that I know that an inverting amplifier looks something like this here. So let's go draw this. So the first thing I'm going to do here is I'm going to build the first stage. So here I go. So the first stage looks like this. I'm going to start off with some voltage value, which I'm going to call V1. Now I'm going to stick that into an amplifier. So that means I have a resistor. I have one that goes here. And note that an inverting amplifier, look what's special about it. V2 is connected to the ground. And it's that little baby right there that gives you the minus sign. And then I have this resistor. And then this is going to give me my V out right there. So what I have here is that I have R1 and I have R2. So if I do this, then this tells me here that the output of the stage is then going to be R2, R1 times V1. So I got to set R2 and R1 so that it has a gain of 5. So in this case, I could pick up anything. So what if I have 100K over 20K? And that's going to give me a minus 5 V1. So now I'm going to set this guy to 100K, and this guy's going to be set to 20K. So what I'm seeing here is that this output node is now going to be minus 5 V1. So now I'm going to set a second stage. I'm going to use a summing amplifier. And when you look at the summing amplifier, look what it looks like here. So if you go in here and I just grab this, let me just grab it and bring it into my, okay, I didn't do a good job there. Let me move this out of the way. So if I bring in my summing amplifier down to here, what you're seeing here is that the output is the sum of these guys. So here's what I'm seeing here. So one of the outputs that I'm going to set here is I'm going to set one of them to minus 5 V1 because that's what we calculated right up here. That's the output of the first op amp. So then it says, come in here, set resistor. Ooh. Is it okay if I call this one? How about if I call this guy R3? And then there's a second one, which I'm going to call V2, and I'm going to call this with resistor R4. And then if you look at this thing, this guy now goes into here. How about if I do it this way? This guy now goes into the op amp, which is then connected to the ground. Remember, if the non-inverting terminal goes into the ground, you're always going to get a minus sign. And now this guy here is the feedback resistor. And so they're telling me that if I get this output right here, this output, according to what they say here, is going to be minus, look at this, it's going to be RF divided by R3 times whatever source voltage I have, plus RF divided by R4 times V2. And since I only have 2, it's going to look like this here. So now you could see here is that I got to choose. So now I choose resistor values where RF and R3 has to be 1 and RF and R4 has to be 2. So if I choose, let's see, if I want to make this 2 here, maybe one choice that I could choose here is I could choose RF to be 40K, which then that implies that the only way for me to do that is to get 20K. But then RF has to be the same no matter what. So if I now look at this case here, RF, if it's 40K, then I'm going to choose R3 to be 40K. So then when I look at the output voltage, you could see here that the output voltage is then going to be 40K, 40K times minus 5V1 minus 40K, 20K times V2. So then the output is going to be plus plus, which will give me 5V1 minus 2V2. So if I draw the whole circuit out, what do I actually see? Well, it's going to look something like this here. The circuit here then comes in and it looks like this. I'm going to have a V1 source. And the way I set this up, what were my resistor values? They were 20 and 100K. So I'm going to have 20 and 100K. And this is the first op amp. And this output right here, right? So if I look at the node right here, this node for op amp number 1 is minus 5V1. That's what that node is. And then I'm going to keep summing this. Look at my picture here. So now this guy has a second resistor, right? Look at that second resistor. And then there's a second input node, which has a resistor connected to this here. And so when I'm looking at this guy here, this guy then has my second op amp, which that is connected to ground. And then I have a feedback resistor that looks like this. So what we said here is that I named the R3 and the feedback to 40. So I know that this is 40K, this is 40K, and the one for the other one is 20K. And so this then gives me the second output node. And the second output node tells me that V out is then going to be 5V1 minus 2V2. And that's an example of how you would set an op amp, sort of like a design an op amp circuit right there. Yeah, this stuff is pretty cool. I agree with Jason. So I got bad news for you. I've now finished this chapter. So that means when we come back, you'll have homework and a quiz. But I'll delay it till Wednesday because I assume after a week off, you're probably either drunk still from the week, or you're in shock that you gotta get back to work again. So I'll set it for Wednesday to give you some release time, but warning, okay? The next few chapters are serious chapters, not something you want to mess with. The problem-solving skills, the interpretation that you have to have is at another level. You know that wonderful node and mesh, the hammer? All that shit is gone now. You can't use it anymore. That crutch is gone. Okay, I'll see you guys later. Thanks for showing up. I appreciate that.
You're hinting, Carlos, that these
Tuesday
circuits
Lab
won't be
people, I
linear
probably
anymore.
won't see you till after spring break. I hope you enjoy it. You Friday people, I'm not seeing you either because there's no lab this week. Hopefully I find out tomorrow whether the equipment is there. I hope to God it's there. If not, I'm in trouble, like big time. But they're telling me that they think it's there, so we'll see. But I'm going to pass some equipment out during spring break. So if you're around, try to pay attention, and I'll give you an oscilloscope and a function generator, one of the old ones, because I don't have enough of the new stuff here. Okay, I'll talk to you guys later, man. Enjoy your
Yes.
break.